Welcome to a little video segment describing the basics of electric dipoles. And this is a topic that can just become a muddled mess of diagrams and equations for students that are new to them. And my guess is this is probably a new topic for most of you. You may have heard it described once or twice in some way in maybe a chemistry class, but I'm going to give you a physics lesson that describes what they are and why we bother to study them in physics. It's actually very easy to describe what an electric dipole is, and it's probably even easier if you look at the diagram that accompanies this. An electric dipole is simply two equal and opposite charges, so we'll indicate that with a red and a blue circle there. Usually we just call them point charges. And they are close enough to each other so as to behave as one thing. So you couldn't have a proton on one side of the room and an electron on the other side of the room and really consider that a dipole. Usually they are a simple model for something that is a little more complex. This also describes why they're important. A water molecule can be modeled as a sort of electric dipole. It has a clear positive end and a clear negative end. You might remember the Mickey Mouse shape that you learned about in your first chemistry class that we used to show the water molecule. And if you remember why you studied that in chemistry class, that also answers why they're important. Water molecules, because of their properties as dipoles, have a tendency to spin when we put them into things like microwave ovens. And we'll talk in a few minutes about why they spin that way. They're also important because other mechanical things like antenna can be described in terms of dipoles. We're also going to describe later in this course how magnets behave very similarly, and we'll call those magnetic dipoles. So these things are pervasive throughout not only physics but chemistry as well, and that I think makes it worth knowing about them. Now the way they're described is also probably best illustrated using this diagram. Because there's a basic definition of every electric dipole, that it is an equal and opposite charge located some distance apart, that kind of shows what two aspects make one dipole different from another dipole. And we describe these by a characteristic known as the dipole moment vector. The dipole moment vector is indicated with a P. You got to be careful here because in mechanics we use P, the vector symbol, to indicate a momentum vector. Now we are not going to be in any way relating momentum with electric dipoles, so we won't have to worry about getting those confused, but it is just part of the alphabet soup in physics that you have to keep straight. So the dipole moment vector is a quantity that describes how one dipole is different from another dipole. And the only things that can make one dipole different from another is how much charge is in each of the point charges, and that Q there represents the amount of positive charge here and also the same amount of negative charge over here. So it's not the total of the two charges, because of course that's always going to be zero when you're talking about a dipole. The other thing that makes one dipole different from another is how far they are separated from each other. Now in different textbooks and in references you'll find this described different ways. The author of our textbook describes this by the symbol S. S is for separation. And so what we call the dipole moment vector has a magnitude equal to Q times S. Now because it's a vector, it also has to have a direction. And this can be a little bit confusing, but it seems simplest to describe the direction of a dipole as the direction that goes from the negative end of the dipole towards the positive end of the dipole. So in this example here, because our negative charge is on the right, That means our dipole moment vector goes from right to left. So that's an indication of its direction. And what can be confusing about this is notice that an electric field always starts on a positive charge and goes towards a negative. But we're not describing the electric field here. We're describing a property of the dipole, and it just, for reasons that will be more clear later, is easier to describe the direction of that going from negative to positive. That might be the single most confusing aspect of this for students who are new to it. One of the things which students are often asked to do is to find the electric field that is associated with a dipole. It's actually indicated here on this diagram with field lines, always of course pointed from the positive towards the negative charges, but we're going to try to mathematically describe these. And when you're asked this, you have to know whether you're dealing with a location that is close to the dipole or relatively far from the dipole. Because when you're close to the dipole, you can just treat this like every other electric field question you've been asked when you have multiple point charges. For example, perhaps right in between the middle of the two charges, or off to one side, or just outside the dipole on the axis. Even on the bisector is a very typical example. But you could do something up here, perhaps in a corner. And all of those entail nothing more than the superposition, the adding of the two electric fields that are produced by the two individual charges. It involves a little vector addition, but that's not anything beyond what you should be able to handle. It's when you're asked for the electric field far from the dipole that you have a little bit more work involved. And that would be, for example, if we say, well, what about way out here, far away, or way out here on the bisector, far away. Now the way far away is described is a little bit ambiguous. There's no set distance that is considered close versus far away. You have to remember that dipoles are described partly by the separation between the two charges. We call that S. And the distance where we're trying to find the electric field is denoted by R. So R, for example, always goes from the center of the dipole out to the location where you're asked to find the field. So when we're asked about those far distances, we can use something known as the binomial theorem. It's a math approximation that makes a rather ugly expression become a whole lot simpler, but it's only appropriate if this distance R is much greater than the separation distance S. And it's in most textbooks it's shown pretty well how they're using the approximation, but it's also something that you can look up on any math reference site or typically in a calculus book, because it's used commonly in a calculus course. So if we are on the axis far away, again on the axis is the dot that I symbolized up here above, it turns out that when you add the effects of the two individual charges out there and you use that math approximation, you get an expression for the electric field that is written probably most simply as 2K times QS over R cubed. It's a rather unusual and surprising relationship because for a single point charge you have an inverse square relationship. But here when you have a dipole, again those charges are relatively close together, the field falls off much more quickly, in this case as an inverse cube. You also notice an important characteristic of this expression is that it has the product of Q times S in there. And Q times S, remember, is what we refer to as the dipole moment vector. So it's not uncommon at all to see this expression written with the P rather than the Q and the S. I hope it makes sense that the electric field is proportional to the separation. If the separation of those is very, very tiny, then that means that the two fields are, I guess, canceling each other out more significantly, and that field will be smaller. But as those charges separate from each other, then you have less canceling effect. And so as S goes, so also goes the electric field on the axis. Now on the bisector, we have a very similar kind of relationship. It's still an inverse cube relationship, but it's just k qs over r cubed. So half the electric field that you would get if you were on the axis. Now, does it seem unusual that being on the bisector would give you a smaller field? Well, I want to remind you of something, and I'm going to draw in a couple of vectors to help you here. The electric field associated with these charges is just the sum of the two individual ones. Well, this positive charge is creating a field that is away from it, and so something like that. The electric field is producing a field out there that is towards, and so it's like that. Now, if you remember the idea of canceling components and adding components, because we're pretty far away from those charges, most of that field cancels out. In this case, it's the two horizontal components that cancel out. The net field, and what they've indicated here with their field lines, and I'll just draw in red like they did, is an upward field. I didn't draw that quite perfectly, but that would be the net field of those two in orange. So that's a rather small field when you consider just the two upward components being added together, and most of the vectors are being canceled out horizontally. So that's why we get a smaller field. And again, this is commonly written with the p vector, and so you can simplify this as just k p over r cubed. And the direction of that, notice, is along the same line as the dipole moment vector, except opposite in direction. The dipole moment vector, the way I have it oriented on the page here, would be downward, but the electric field on that bisector is upwards. So you will find some expressions that show that just by putting a negative sign on the expression and then putting the vector symbol over top of the p. That's just a matter of preference. So you got three different options for calculating the electric field, and you really just have to know what location you're asked about. Are you asked close by? Are you asked far away on the axis? Or are you asked far away on the bisector? And then you just use the appropriate method. Well, I told you back when we started that I would try to give you some motivation for why we bother studying the behavior of dipoles, and now we're to that point. And really they become interesting when we take a dipole and we place it inside some other electric field. Just to be clear here, I'm referring to not the electric field of the dipole itself, but another electric field produced by some other charges somewhere. And most commonly and most simply, we put it into a uniform electric field. So I've indicated that electric field here with the upward red arrows, and the field for the dipole itself I have not bothered drawing just because it would clutter the picture so much. But let's remember what any charged particle does when it's in an electric field. It has a force on it, and if it's free to move, then that force will cause an acceleration. But remember, a dipole is not just two individual point charges, although that's really how that's made up. There is something that is tying these two things together. So we're not going to stretch the dipole or anything like that. So let's take a look at what the force would be on each of these particles. And there they are, indicated by F1 and F2. The positive charge would be pushed in the direction of the external field. That's the one on top there. And the blue negative charge has a force on it that is opposite the direction of the electric field it's in. So because they're identical charges in identical fields, those forces, F1 and F2, are equal to each other and opposite in direction, and therefore there is no net force. And that's why we will not find the charged particles or the dipole actually moving up, down, left, or right. But do you recognize what those forces can do? What they can do is tend to rotate this dipole about an axis right in the middle. And so it's that rotation that causes these dipoles to spin when they're placed into an electric field. And the way we describe how much spin they get is in terms of torque. So I'm going to remind you that torque is described as a vector cross product of an R crossed with F. And the R vector is a vector that goes from the axis of rotation to the location where the force is located. So that's half the length of the actual dipole itself, or half of S. Put that S over 2. And the force, well, the force is just Q times E. And so when you look at what we have there, we've got a torque on the top one that's equal to that, and a torque on the bottom one also equal to that. So we're going to double this to get the net torque. And so we get a result when we cancel out these 2's of S times Q times E. Well, what is S times Q? That's what we've defined as the dipole moment vector. So the easiest way to describe this is it's the product of P, the dipole moment vector, times E, and the other factor that we haven't taken into consideration yet is the cross product. And so we'll put it in like this, P cross E. Both of these, P and E, are considered vectors, and torque as well. And so to see why the cross product is helpful here, I'm going to look at one other figure. Let's consider what happens, and this is my more crudely drawn diagram. What happens when this dipole spins around clockwise to the point where the positively charged particle is now directly above the negative? We still have the upward external field. I've indicated that rather than with a bunch of little red arrows, just one big red arrow so it doesn't get in the way. Well, now we've got forces that are still in the direction or opposite the direction of the electric field. I still have no net force on it. It's almost like a tug of war. But we also at this point have no net torque because there's no force that's actually perpendicular to the R vector. So this perpendicularity factor is actually very important when we're describing how much torque we get on a dipole. If we place the dipole in the field as it's indicated here in this last picture, well, we're not going to get any torque at all. And how would we get the most torque? Well, we would have to have the dipole moment vector completely perpendicular to the electric field. That would be going a little closer to what we had in the first diagram. I'll show you up here. That was placed in about 45 degrees. If in this figure we had placed that in a perpendicular orientation so that the dipole was horizontal, that's when we would get the most torque. So seeing how dipoles can torque in an electric field, and considering the simplest case, which is a uniform field, just scratches the surface of what these things can do if they're in non-uniform fields. Our book addresses that a little bit, but that's not really anything that I need you to worry too much about. So just to be able to describe the torque, how it comes about, and that's probably sufficient for what you need to do. So hopefully this has been a good and helpful little primer to what electric dipoles are, what makes them important, and how they behave in an external electric field.